In this lecture, we talk about column orthogonality of the character table. So we start by defining the centralizer. So you fix an element G of the group. The centralizer is the set of all elements of the group which commute with this fixed G. So all the elements of the group which commute with this fixed G, and we write it like this. Now an important fact. So first you fix an element G of the group. Then you can talk about two things. First thing you can talk about it is conjugacy class, and the second thing you can talk about is the centralizer. So the question is, how is this size of the conjugacy class related to the size of the centralizer? So this there is an important fact which says that the size of the conjugacy class has the index of the centralizer. So that is G divided by the size of the centralizer. So we have a finite group G, so this would make sense. Or you can transfer this to this side, so you have the size of the centralizer is same as the size of this G divided order of the group divided by this conjugacy class. So size of group divided by the conjugacy class. So now we come to the proper theorem. So let this chi1 to chi k be the complete list of irreducible characters of some finite group G. So then for two elements G and H and G, so we have two possibilities. Either this G and H are conjugate, so if they are conjugate we are in this case, or G and H are not conjugate, in which we are here. So then this sum of these characters, so we are going from 1 to k, you're conjugating the first character and keeping the second one as such. This is 0 if G and H are not conjugate, and it is the order of the centralizer of this group G if G and H are conjugate. So first, immediate corollary. So if you take G and H as 1, or you can put it as E in a group, then obviously both of them are conjugate. So we are working here, but if G is just E, then all the elements of G would commute with this E. So the center of the group is just the entire group itself. So this becomes G right here. And here you're putting in 1, so this comes here 1. But you know this of identity E, this is just the dimension. So this is just the dimension, so dimension of Vi square. So we get this relationship, order of G or the size of G is the square of the dimensions, this Vi. And we have seen this before. So before we start proving the theorem, let us see this in action on this symmetric group S3. So now we can talk about group elements here. So in terms of conjugacy classes, there are three classes, one corresponding to the identity, then one corresponding to this 1, 2, and one corresponding to 1, 2, 3. So we are taking this G, putting it as E. Here this G is 1, 2, and here this G is 1, 2, 3. So first our trivial representation, this is 1, 1, 1. Then the sign representation, which is 1, minus 1, and 1. And this third representation will just come from, you just see how many elements are fixed. So this will come from number of elements fixed by S3 minus the trivial. And this will make sense in the next lecture when we will talk in detail about how this would give an irreducible representation. So this is an irreducible representation, we'll talk about it later. So now you know that all the elements are all the elements are fixed by the identity for S3. So 1, 2, and 3, all of them are fixed. So 3 elements are fixed, and 3 minus the trivial gives you 2. Now with 1, 2, 1 and 2 are permuting, so only thing fixed is 1. So one of the elements here is fixed, which is 1. So this is the fixed by S3. So only 1 is fixed, but then 1 minus 1 is 0, because you're taking fixed by S3 minus the trivial. 3 minus 1, 2, 1 minus 1, 0. And here 1, 2, 3, all of them permute. So number of them fixed by this element G is 0, because all of them are permuting. So 0 minus 1 gives you minus 1. So this is how we get the character table. So now our observations corresponding to this. So first look at the dimensions here. So this is the dimensions. So 1 square plus 1 square plus 2 square, this comes right here. So now we are using this formula here. So you get this is 6, which is precisely the size of S3. So now our group is S3, and we are talking about the conjugacy class, size of the conjugacy class with respect to identity. So this is the size of the conjugacy class, which is 1. So you just get S3. So now you take these terms here. So now we are working with this formula right here, this formula right here. So these are in the same conjugacy class. So these were in the same conjugacy class. Now these are in the same conjugacy class. So all of them are real. So if you do like this, you're just going to get square of the terms. So you get 1 square minus 1 square 0 square, which gives you 2, which is precisely S3. Size of S3 is 6 divided by size of the conjugacy class, which is 3. So 6 divided by 3, which gives you 2, which is size of this class. So again, this formula is right here. So you get 2, which is just 6 divided by 3 here. Similarly for this, now you focus on this conjugacy class. So everything is real. So you just multiply and you square the term. So 1 square plus 1 square minus 1 square gives you 3. And this is the size of your centralizer. Basically you have 6 divided by size of the conjugacy class is 2. 6 divided by 2 gives you 3, which is the size of the centralizer. So this is the size of centralizer. So which obviously, notice that our group element G here. So notice that this G here is 1, 2. The G here is, in this case, is 1, 2 and 3. So this is the first thing we notice with respect to our theorem. The second thing is column orthogonality. So this was within the same conjugacy class. So we were working here, G and H were conjugate. Now if they are not conjugate, you should get a 0, and that's precisely what it is. So 1, 1, 2, and then you do the first two columns, this and this. So column 1, column 2. So you're taking the inner product. So you get 1 times 1, 1 times minus 1, 2 times 0, you get 0. So here now you're doing the first and the third column. So you have column 1 and column 3. So 1 times 1, 1 times 1, 2 times minus 1 gives you 0. And here we have column 3 and column 2. So you have column 3 and column 2. So column 3 is this 1, 1 minus 1. So you 1, 1 minus 1, or you could say 1 times 1, 1 times minus 1, minus 1 times 0. So add it up, you still get 0. So we have talked about this case, this zeros which stay right here, because now we are taking cross column. So we are in different conjugacy classes. And if you are working in the same conjugacy class, then you're taking the squares, and then you're getting the size of the centralizer. So you're getting the size of the centralizer if you are in the same conjugacy class. So this is same conjugacy class. So now let us see the proof of column orthogonality. So for the proof, you start by saying that let X be the character table, and this character table is a square, so which we have seen before. So X is a character table with the square matrix, and the ijth entry is this chi I of gj. So this is from the conjugacy class. So you're not taking all the group elements, you are just working with conjugacy classes. So as we have just seen in the character table of S3, that how you did not work with all elements of S3, just with the conjugacy classes. So now you take the inner product. We know this inner product is either 0 or 1. So orthogonality of characters here. So you have the orthogonality of characters, which we have proven before, right here. And now you use the formula, but you are using these G's as the elements of the group. But as I just said that, you do not work with all elements of the group, you just work with the conjugacy classes. So this is constant on the conjugacy class. So now we work on the conjugacy class instead of this group, this R here, Instead of this group, you're working with the conjugacy classes. This G comes in, and therefore since you're working with the conjugacy classes, you have the size of the group here. Now this comes right here, this comes right here, because this obviously this xjr is nothing but our chi j g of r. So essentially this notation is coming right here, but this r corresponds to the conjugacy class. So now this is the corresponding to the conjugacy class. Maybe I should write it like this, in the conjugacy class. So these two are coming here. Now this is precisely the size of the centralizer, and that's what we are using here. So just taking reciprocals here, you get the size of the centralizer here. So now this is again delta ij, so which is 1 for I equals to j and 0 otherwise. So now you do it for all the characters like this. You get identity matrix from here. This gives you x bar, this gives you transpose of x, because this is ir and jr, and this d inverse corresponds to this, so which is cg1 and so on. So this is what we get. So this is kind of simple matrix algebra, simple matrix multiplication, and we have done nothing. We have just put this 1 over cg like this, and this corresponds to this, this corresponds to this. So what we want to prove essentially is that this conjugate transpose with x is d. So what is it? This is basically, this becomes, is saying this chi I gj times chi I gk. This is 0 if you're not conjugate, you're not in the same conjugacy class, and if you're in the same conjugacy class, then it is this, which essentially is the proof of the theorem here. So if you're not conjugate, you are 0, as you can see, and if you're on the diagonal, you're conjugate, then it is this. So we have to prove this, and that will result in the proof of the theorem. So proof would end, and this is easy to show. Now this we have already seen. This is just following our nose. Now the only thing we need to notice is this is the size. So if you take the conjugate, so think of them as complex numbers, but now they are real numbers, you take the conjugate, is the same. So you get this. So you're conjugating all the entries, you conjugate d inverse, you still get this. So now you start conjugating this. So you conjugate this, so you get x double bar, which will just give you x. Conjugate this, you get d inverse. Conjugate this, you get x bar of t. And conjugate identity, you still get identity. Or in other words, now you multiply both sides by x. So you multiply by x here, multiply by x here, you get this, and you get this. Now you bring these two to this side, and that will be the end of the procedure. So because now you will multiply this side with x inverse, and then you cancel, get identity, transfer d here. That gives you the proof.